Good afternoon, class. This is the week 9 Monday lecture. We're going to do another example problem on the method of joints, and then we'll introduce a new technique called the method of sections used to solve actually individual members within a truss, where you wouldn't have to use the method of joints. So this is the week 9 Monday lecture. Method of joints, I have a fairly simple truss. It forms a square shape with one diagonal. There's a reaction at A, which would have an A sub y and an A sub x. We have two forces, external forces, acting at B, 250 newtons directed in the positive x direction. We have 200 newtons acting down negative y direction at B, and then at D we have 400 newtons directed in the positive x direction, and we have 300 newtons acting in the negative y direction. Normally we would solve for the reactions first, and you can do that in this problem, but the way this problem is configured, I can just use joints at D, B, and C and solve for all the members without having to solve for any of the reactions. And in fact, these will be extremely simple. You can almost do these by inspection. So I'm going to do this without solving for any reactions. So I'm going to go to joint D. Here we have the 300 Newton force acting down. We have 400 Newton force acting in a positive x direction. I show DA going into the joint compression because the 300 is down, and I'm showing DC again going into the negative x direction. The external force is 400, and in the x direction positive. Okay, and just by inspection, I know DA has to equal the 300 newtons compression, and I know DC has to equal 400 newtons compression. Okay, I can write this out. Sum of forces x equals 0, DC is equal to 400 newtons compression. Sum of forces in the y, dA has to equal 800 newtons compression. And if you just said by inspection, it's equal, that's fine. I just write the sum of force x equals 0, sum of force y equals 0 to make it real clear. Okay, so I write those answers in here. Okay, 300 and 400. And then I'm going to go to joint B, which is going to be absolutely the same configuration. Okay, joint B, I have the 250 Newton external, 200 Newton, negative y direction. BA has to equal 250 newtons tension. BC has to equal 200 newtons tension. Again, I sum forces in the x, sum forces in the y. Just by inspection, I can see that. So I can go back up to joint C now. I've got the 200, 400, the C sub x, and then I have the C sub A. I'm going to show that as tension. The slope, it's 2 meters horizontal, 2 meters vertical. It's 1 to the square root of 2. So I go to joint C. And this is my free body diagram. My C sub x, 400 in the x direction, positive x, 200 negative y direction. And then I have 1 to 1 square root of 2 C sub A. So I sum forces in the y, minus 200. I directed this in as tension, and so the y component is going to be negative 1 over the square root of 2 C sub A. C sub A is 263 newtons. I get to 263 newtons, and it's negative, so it's compression. So I'll write that as 263 newtons compression. Done. I solved for C sub x. You didn't have to. That's a reaction. Reactions weren't necessary. And so actually took maybe 3 or 4 minutes once I got this set up to solve for the members in this particular truss, the force of the members. So this is the extreme on the other way, where you get a really fairly simple truss. The example we did in the last session, a little bit more complicated. That's typically what you would see in a truss, maybe something like the other one, but you can run across these, and once you recognize them, take advantage of the methodology. Okay. So now we go to the method of sections and what that means. Got this fairly complicated truss structure, might be typical of a rail bridge. We got members from A through R. I've got loads at all the panel points along the bottom. I show these as forces. They could be the same, they could be different forces, it doesn't matter. I've got a pin at A and a roller at K. And for some reason, the question says, I don't want to know anything about all these members. What I want to know is what's happening only in this section EF, EG, or EO, and PO. So I just want to know what's going on in this member, and this member. If I give this on a test, I had some students then would start here and use the method of joints, and it takes you a lot of work to get to here. And method of section says we can do this very simply with one free body diagram. Okay. So this truss is in equilibrium. What I'm going to do is pass a cutting plane. I'm going to cut this truss through EF, EO, and PO. And then at that cutting plane, I'm going to separate this truss. I can do this to the right, and I can do this to the left. It's just separated. It's now suspended in space. If the truss is in equilibrium, this exposed section is going to have to be in equilibrium. So what we've done is we know there are internal forces. That's what the method of joints allows us to solve. There are internal forces in all the members. When we cut this and look at this section, these internal forces are now exposed forces. Okay, they're cut, they're now exposed. They're not internal, they're external. And since the entire truss is in equilibrium, this section is in equilibrium, as is this section is in equilibrium. Okay, that's what equilibrium is about. Okay, so the exposed section is in equilibrium. So what this method allows us to do then is to draw a free body diagram of this section. And I can choose to go either to the right or to the left. I'd probably go to the left because there are less forces than if I go to the right. So here's my free body diagram. Okay, truss looks the same out to here. And then here are my cut sections. Now the forces aren't internal, they're external. So here's EF. And I'm going to show all of these as tension. I can't look in here. It's impossible to tell whether it's tension or compression. So definitely when we do method of sections, show everything to begin with as tension. So here's EF, here's PO, and here is EO. Okay. Solution technique. I can take moments about O. So it takes this force out, EO out, PO. All I'm left with is EF. It's a simple moment equation. We got forces and we'll have dimensions. So what I can do then is solve, once I take moments about here, I can solve for EF. So I'm going to solve for EF. About this point, I can also take moments about E and solve for PO, okay, which is what I did here, PO. Or I can go off and take moments about O and solve for EF. Or I can use sum of forces, say once I come here and solve for PO, I could sum forces in the Y and some forces in the X to come up with the solutions for the other two forces. You'll always have one extra technique to check, always. So if you use a moment in two force equations, you've got an additional moment equation depending upon where you start. If you use two moment equations, you'll have an additional force equation to also check. So you'll always have a check. Okay. So let's take a look at an example problem. Have a truss. A, B, C, D, E, F, G, H. Dimensions 2 meters, 4 at 2 meters, 3 meters. So the slope on the diagonals will be 2, 3, square root of 13. And what I want is the force in BC. I want the force in BG. And I want the force in HG. And what I want to do is use the method of sections. So I pass a cutting plane through this section. And then I want to draw the free body diagram. So I'll come down here and draw the free, and we have to also solve for reactions, which I did. Okay, sub y is 9 kn, a sub x is 8 kn in the negative x direction. So we always want to solve for reactions here. This will be part of our free body diagram. So I'll draw the free body diagram. So here's the 9 kn. Here is the 8 kn. Now here are my cuts, and the exposed forces, internal forces, are now external. And I'm going to show all these as tension. So here's BC. Here is HG. And this is my BG. And the slope is 2, 3 square root of 13. What I'm going to do is take moments about B equal to 0. Which takes out BC, and so what I have then is HG. Okay, this dimension is 3. This dimension this way is 2. Okay. So I have HG, and HG is going to counterclockwise around B, and its moment arm is 3. So it's going to be positive. So HG times 3. And then I have the 9, which is going to rotate around B in a clockwise direction. Okay. And its moment arm is the 2. So it's minus 9 times 2. And then the 8 is also going to rotate in a clockwise direction. And its moment arm is 3. And that's equal to 0. So you get Hg is equal to 14.0 kilonewtons. And that's tension. Now to get here, I can do sum of forces in the y equal to 0. I have a 9 positive. Y component here is, it's going negative y. It's negative 3 over the square root of 13 BC. Equal to 0, which says BC then sorry, that's down to G. I can write that as T. That's BG. It's going down to G. So that's BG is equal to 14 kN. And that's tension also. And then I can do sum of forces in the X. Equal to 0. Okay. BC in this direction, HG, which is 14 plus 14 minus the 8. And then we have this component here. This will be a negative We gotta have the X component here. Okay. Which is going to be 2 over the square root of 13 for this one. 2 over the square root of 13 times BG, which was 14. Equal to 0. That gives us BC then. It's equal to 12.0 kilonewtons. If this BG comes out to be, I did that. This comes out to be 10.8 kilonewtons. And so this, that one comes out to be 10.8 kilonewtons. And so BC is equal to 12 kilonewtons down here. So method of sections. The last thing I want to mention to you, and this is important for exams and stuff, is this concept of symmetrical loading. So I have a truss, and if you notice, the loads across the lower panel points are all the same, 100 pounds. Symmetrical loading says if you can divide this truss exactly in half, which we can at this particular point, and the shapes and dimensions are the same and the loads are the same. Okay, in other words, they match each other. In other words, this section to the left is identical to the section to the right. Of course, we have a pin and a roller that's out, it's still loading. Okay, so this is what we call symmetrical loading. And if this was a problem, and I asked you to solve for this entire truss, and this is the symmetrical loading, what this means is that the force and corresponding members are the same. So the force in BK is the same as the force in Fi. The force in CK is going to be the same as the force in EI. And so on. Force in KJ is the same as the force in JI. So KJ is the same as JI. This force is the same as this force. This force is the same as this force. And so on. It's symmetrical. So basically what you do is you solve for half the truss. You've identified it as symmetrical. You have to say that. And then just transfer these forces to its corresponding member. That's what symmetrical loading is all about. Also, we do have some zero load members. One, this is a zero load member. This is a T intersection, which means that this force is 0. So what you'd have to do, this isn't anything corresponding in here. Identify that to begin with as a zero load member, and then the symmetrical loadings work, solve half the truss and just replicate on the corresponding member on the other side of the truss that you're looking at. So that's how we deal with symmetrical loading. Suppose this is a railroad bridge. I don't know if any of you thought about this. So we've got tracks, got a train running across here. Again, the only way we can load this is at these panel points or joints. Well, we have a set of tracks running across here. Think of this in the third dimension, and you got a train running across here. Well, if this is a highway bridge, got pavement, got cars. Question is, are we not loading across this entire structure? How are we getting loads at these points only? Well, we use what's called a system. Well, they have different names depending upon what technique you're using to design and what it is you're designing. I'm going to call this runners and stringers. So I'm going to draw this looking down. So I'm going to see a line on both sides of the bridge. Okay, so, keep in mind as we do this, and if this is a working structure, you'll have another structure like this, okay, in this direction. So I'm looking down, and here are the tops of my two trusses. And here are my panel points. Or my joints, or my pins. Okay, so here we have where the loads are going to occur. So what we're doing is we're running a load across this entire structure here. And somehow these loads are being transferred here and here. So we have what I call a system of, I call them runners and stringers. So I'm going to have beams. These are my runners. And as we're moving a load across here, or bridge deck or rails, whatever, I'm transferring that load to these beams. Okay. And the way this works is I'll just show you one example. The load from here, center line to center line, is taken up in this beam runner, and so on. I mean, it splits this in half. So these are collecting the loads in this direction. Then what I'm going to do is run stringers in this direction. Okay, so these basically are going to be complicated structurally, but they're going to be underneath. Okay, so I've got stringers this way. Okay, So these runners are on top collecting load. So what happens is each stringer then, let's see, I've got 1, 2, 3. I want this to be 1, 2, 3, 1, 2. Say I've got 3. It's uniform across here. So this part of the stringer is going to take this load and this load here. It's going to transfer to this girder runner, which is going to take the load over here to this pin. So half the load. This part is going to take this half plus this half to here. This one's going to take half here, and so on. It's going to take half over here, this half be transferred to here, which will run out over here. So basically what we're doing is we're transferring this load, say in the X direction, okay, we're then transferring in this Y direction, either way, in equal amounts. Okay, half the load on either side goes to this stringer, and then half load over here on each side goes to this stringer, and then it just continues on. Uniform distribution of load. And that is basically how, well, quite a bit more complicated than that, but that's the idea of being able to transfer loads where you get load points only at the panel points or the pins or the joists on this thing here, runners and stringers. Okay. So as we continue on, we've talked about zero load members. We've talked about method of joints. Talked about the method of sections. You've talked about symmetry, loading symmetry. We emphasize the fact that in most cases you need to solve for reactions, and you should always check your reactions. Absolutely check your reactions. Okay, what we don't want is we don't want your reactions to be wrong, and then your truss is wrong. So always check your reactions as you go through these problems. Always. And you always have a check calculation that you can do, for instance, on reactions, so you know you've done your work correctly. I'll review these things again, but these are some of the highlights, the points that we tried to make so far in this chapter and in the problems that we're working. They can apply to other problems too. So just be aware of all this as you go through the work that you're doing. Make sure you know how to do these trusses on your own. Okay. basically they're done all the same way. Doesn't matter what the configuration is of the truss, the method is the same. And again, all you're doing is adding and subtracting some forces, X and Y. A little bit different in when we use the second method of sections. You may have to use typically you would have a moment equation in there, but method of joints, it's all adding and subtracting forces, X and Y direction. Okay. That ends our discussion for this particular lecture.